Hey everyone, welcome to BCP Med. In this video, we're going to be taking a look at resonance structures, specifically the theory behind how resonance structures work. We're going to be looking at orbitals, graphical representations, what makes an optimal resonance structure, and how lone pairs factor into the resonance structure process. Let's go ahead and get started. So, first and foremost, what is a resonance structure? Well, resonance structures are different graphical representations of the pi bond connectivity, that is, the double and triple bond connectivity, in the same molecule. In other words, resonance structures are different ways of representing how the pi bonds connect different atoms within a given molecular structure. For example, consider the molecule NO2. One way of representing the molecule NO2 is in the Lewis structure shown below, with a negative charge on the oxygen on the left and a double bond connecting the N and the O on the oxygen on the right. Another way to represent the NO2 minus anion, though, is with this Lewis structure, with the double bond on the left and the negative charge on the oxygen on the right. These two are not different molecules, right? They're not two of the same molecule. They are actually the exact same molecule drawn two different ways, right? Cannot stress this enough. They are not different molecules. They're not two of the same molecules. They are the same exact molecule, just with the electron density represented in two different ways. In one case, showing the pi bond on the left atom, and in one case, showing the pi bond on the right atom. Another structure to help us visualize this is this structure here, N2O. In one resonance structure, we have the triple bond to the nitrogen on the left and the negative charge on the oxygen on the right, whereas in the right-hand structure, we have two double bonds, one to the N and one to the O, with a minus charge on the N. Both of these structures describe the exact same molecule. However, they represent the pi electron density and the connectivity in two slightly different ways. Which one is better and which one more accurately depicts the orbital picture of that molecule is not trivial, and we're going to go ahead and break that down now in the following slides. So it's important to understanding resonance structures to first understand what exactly a pi bond is. I'm going to go ahead and remind you that pi bonds form when you have two p orbitals which are parallel, each with an unpaired electron. These p orbitals can go ahead and form a sideways overlap, right? We know that the sigma bond, which is this line between the two atoms, is formed by end-over-end overlap. However, those p orbitals that are left over after the sigma bond forms can go ahead and overlap sideways to form this pi orbital, or this pi bonding orbital, which has a shape that looks sort of like the structure on the right, where you have electron density over the top and the bottom of those two carbon atoms. And because of that, because that electron density is spaced out over the top, it leads to some pretty interesting effects. Specifically, when we talk about those interesting effects, it's that the pi bond, or the pi interaction between adjacent p orbitals, can actually have multiple discrete combinations. There's multiple ways that we can put together those parallel p orbitals to form those overlapping pi bonds. For example, let's look at the molecule benzene. Benzene is a 6-carbon ring, each of which is participating in a double bond. So each of those pi bonds is going to be comprised of those vertical p orbitals which are parallel with one another. Notice, however, that there's actually two ways that we can blend the p orbitals. One way would be to blend the p orbitals that are adjacent to one another in this fashion. So we take the bottom two, and then the top left two, and the top right two, and combine them into pi bonds. That's pretty straightforward, right? We're just doing a sideways overlap. But it would be just as correct to combine the top two and then the bottom left two and the bottom right two in the structure shown on the right here. Okay? Both of these are exactly equivalent pictures of the pi bonding system in a benzene ring. So which one is correct, right? Which resonance structure is giving us the correct molecular picture of how the electrons are distributed? Well, it turns out that the real molecule is a combination, or rather a superposition, of the several individual combinations that are possible for the p orbital density. In other words, the overall molecule is a superposition or a combination of all of the different resonance structures. So for example, if we look at this resonance structure where the double bonds are arranged in this configuration, and we combine it with the other configuration where the pi bonds are inverted into the other adjacent p systems, and we combine those two, we would get an overall picture that's this sort of circular ring system, where the electron density is not actually configured in one or the other state. It's a blend of both and is shared across all 6 carbons equally in this cyclic system, right? And that is true of all resonance structures, right? So if we go back to our N2O, we have the resonance structure on the left showing a triple bond and a single bond, and the other resonance structure showing 2 double bonds. So which structure accurately describes the molecule? Well, it's really neither and both at the same time. The real molecule is a superposition, a blend of those 2 structures. The real molecule is more like a N to N 2.5 bond and an N to O 1.5 bond, which is comprised of the 2 individual resonance structures which describe the molecule. We can't really draw a Lewis structure for the combination, so we go ahead and just choose the extremes of the molecular superposition with the pi bonds in discrete orientations to represent in our Lewis structure. But in reality, the pi bonds are not a discrete combination. They're a blend of all the individual possibilities. So how does resonance impact the characteristics of those chemical bonds? I mean, are they the same as a normal double or triple bond, or are they going to be different? Well, it turns out that because the real bonds are a superposition or a mix of multiple structures, it's going to have intermediate properties between that of the individual resonance structures. So for example, if we look at N2O, we said that it's going to have sort of like an N 2.5 bond and an N to O 1.5 bond, right? So that bond on the left is going to be somewhat weaker than a triple bond, right? A triple bond is shorter and stronger than a double bond. So this bond is going to be a little bit weaker than a triple bond, but stronger than a double bond. Similarly, the bond on the right is going to be somewhat weaker than a double bond. It's only about a 1.5 bond, but it is going to be stronger than a single bond. So we can actually measure these properties and find that indeed the molecule is somewhere in between the 2 discrete resonance structures, the N triple bond, the N double bond, and the NO single and the NO double, right? So where things start to get tricky is that there's actually multiple ways to represent the pi electron density of a pi bonded system beyond just the connectivity of those bonds, right? So we already talked about the fact that pi bonds can be represented as this bonded system where the electrons are shared across both atoms. However, in addition to changing where the pi bonds are placed, we can actually completely shift the bond onto one atom or the other. And in separating that, we actually create formal charges. Say we were to shift the pi bond completely onto the atom on the right, we're going to give that carbon a formal negative charge because we're giving it electrons. And we're taking them from the carbon on the left, which is going to give it a partial positive. If we were to look at the orbital picture, it would look like taking the whole pi orbital and moving it onto a carbon p orbital on the right-hand side, which is going to contain a lone pair and a minus charge, and give an empty p orbital to the carbon on the left, which is going to carry a partial positive. These are also considered resonance structures. Specifically, they're charged resonance structures, right? Oftentimes, resonance structures will involve a movement of formal charges and not simply changes in connectivity. For example, if we look at the ozone molecule, we see that one structure has the double bond to the oxygen on the left and a negative charge on the O on the right. But we can just as easily draw it such that the negative charge is on the O on the left and the double bond is on the O on the right. These two are completely equivalent structures, and they both contribute to the overall picture of the molecule. So the real ozone molecule is going to look something like an O on top with 1.5 bonds to both of the O's on the left and the right, where each of the bottom oxygens carries some degree of partial negative charge, since the negative charge of the resonance structures is shared between both of those oxygens, right? So it turns out, though, that not all resonance structures are equivalent. Some resonance structures are better or are more significantly contributing to the overall superposition. So generally, the important characteristics of a resonance structure are as follows, in order of importance. The first is that all period 2 atoms must have full octets. They absolutely positively must. carbon, nitrogen, oxygen, and fluorine should never have less than a full octet. Any structures which do put less than 8 electrons around a C, N, O, or F are going to be very weakly contributing to the overall structure. The next is that formal charges are minimized. When formal charges are present, there's an electrostatic interaction between the negative and positive charges, which tries to get the formal charges to collapse in on themselves, and so that arrangement is inherently somewhat unstable. So formally charged resonance structures are going to contribute less so than non-formally charged resonance structures. Finally, if we have to have formal charges, we want them on the atom that best accommodates the formal charges. Usually that's going to mean placing the negative charge on the most electronegative atom or the most polarizable atom, such that the negative charge is the most stable it can be. It also goes the opposite way, placing the positive charge on the most electropositive element, or the most polarizable atom, such that the positive charge is stabilized. So let's go ahead and look at some examples. So consider the carbonyl group, or the CO double bond, as shown in the molecule formaldehyde. There are a couple different ways to represent this bond. One is the CO double bond as shown here. But we can also actually separate this double bond and push all of the electron density onto the oxygen, which would give us the following resonance structure here, where O carries a minus charge and the carbon carries a positive charge, right? That would be, you could represent that using arrow notation to go ahead and push this double bond here onto the oxygen as such. We can represent that as the bond moving onto the oxygen to give it a negative charge. This resonance structure is going to be less strongly contributing than the one on the left, because while the oxygen has a full octet in both cases, the carbon does not in the second case. And also, we've created formal charges. So we're violating the first two rules, so this is not going to be a very significant resonance structure. However, there's another resonance structure even, and that is the one putting the negative charge on the carbon instead. So if we were to take the bond and instead move it this way, we would obtain resonance structure number 3. This is even worse, because in addition to failing the first two characteristics, we're breaking octets and creating formal charges, we've also now placed the negative charge on a carbon, which is less electronegative than oxygen. So that negative charge doesn't even really want to be there, right? So in ranking, the resonance structures in priority would be as follows. The one on the left would be the best, second best in the middle, and third on the right, in terms of how much they contribute. Another example would be to consider this molecule, SCN. So one resonance structure for this ion, or the SCN minus, I should say, is this structure with an CN triple bond and a single bond to sulfur, where S carries a formal negative, or the structure on the right, where N and S both have double bonds, but nitrogen is carrying the negative charge. So which of these is going to be better? Well, which atom better carries the negative charge, nitrogen or sulfur? Well, nitrogen is more electronegative than sulfur. However, sulfur is far more polarizable than nitrogen. In this case, the polarizability of sulfur is going to be more significant. So sulfur actually carries the negative charge better than does nitrogen. And as a result, the structure on the left is going to be better than the structure on the right. And so the structure on the left will contribute more, and the overall molecule will look more like N triple bonded to C and single bonded to S, rather than equivalent double bonds to both atoms. Another thing to consider with resonance structures is the behavior of lone pairs that are adjacent to the double bonds or triple bonds in a structure. Lone pairs that are adjacent to a double bond are actually located in a p orbital rather than, say, an sp2 or sp3 type orbital for the most part. The reason is so that those lone pairs can also delocalize into the pi system. It's not just double and triple bonds that participate in resonance. For example, let's say we have this molecule, which is called an enamine, which has a nitrogen with a lone pair adjacent to this CC double bond. If we were to look at the orbital picture, that nitrogen will have its lone pair in a p orbital, which is parallel to the pi system of the CC double bond. And as a result, that lone pair can actually go ahead and push itself very nicely into a new double bond and push the existing double bond out, such that it will create a resonance structure which looks like that on the right, where the nitrogen now has a double bond and carries a positive formal charge, and the carbon on the right now has the lone pair with a negative charge. And the orbital picture would look like this. So we could see sort of that the orbitals have swapped. The p orbital on the left has combined with the pi system to create a new pi bond and a separate p orbital on the far carbon. So this is how lone pairs can interact with a pi system. They can themselves delocalize to create new resonance structures. Now, I mentioned this, but I really want to stress that for a lone pair to actually be in resonance or resonate with the rest of an adjacent pi system, its orbital must be parallel to the other p orbitals, to the other pi bonds. If it is so happens that the lone pair is perpendicular or orthogonal to that pi system, the electrons cannot delocalize. When might we have a situation like this? Well, if we have a neutral atom that has a lone pair, but it's already double bonded to some other atom, that lone pair will fall into this category of being perpendicular. So let's go ahead and look at the molecule pyridine, which has a nitrogen that's already double bonded, but it's also going to have a lone pair shown here in red, right? That lone pair, if we look at the orbitals, is going to be perpendicular to the electron that is participating in the pi system. The pi system is going to be vertical in this case, or the p orbitals are represented as vertical, whereas the lone pair is in an sp2 type orbital pointing perpendicular 90 degrees from that pi system. It will not interact. There is no sideways overlap. And so if we look at the molecular superposition, we see that we have that nice circular aromatic ring resulting from the resonance of the double bonds, but that nitrogen lone pair is not participating whatsoever. It has nothing to do with it. So it's really important for lone pairs, once again, to be parallel to the pi system in order for them to be able to form new resonance structures. And with that, we've actually reached the end of the content for this video on the theory of resonance structures. Thank you guys so much for watching, and if you enjoy what you saw, please like and subscribe to the channel. Make sure to check out our other videos on the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists as well. See you next time!